So now that we understand what we mean by electrical insulation systems and we understand what are the basic properties of dielectric materials, I'm going to spend a little time discussing about what are the research challenges that are occupying the research community in terms of insulation. What are we still looking to find? Well, we are looking at new insulation design. And what does new insulation design mean? It means that I'm looking at better materials. I'm trying to develop and apply new materials which are better suited than the conventional materials that I'm using at the moment. Like, for example, I will talk about nanomaterials, I will talk about functionally graded materials, I will talk about various composites. And I am also looking at advanced computational resources that are available to me, which allows us to estimate the kind of stresses that will develop in a system, to understand whether the material or the insulation system will be able to withstand those stresses, and design accordingly. Once you design, you need to make sure that your design is effective, and for that I need testing facilities. As I said, we have a lot of new diagnostic capabilities available with us, which means that we can test features of dielectrics in operation which we could not earlier. We don't have to wait for a dielectric to fail to figure out that it has degraded. We can apply new diagnostic techniques so that we can estimate the health of the system and we can come to a conclusion about its remaining life. So we will be looking at development. We want to be able to develop and apply new materials. We want to design for much higher field strengths, because in that way we will be able to have more compact systems which can be used in special situations. We are also looking at composite stresses, because when you have an equipment in operation, it is not going to be subjected only to electrical stresses. There will also be non-electrical stresses. For example, in conjunction with electrical stresses, there will be temperature, so there will be ambient stresses, there might be mechanical stresses, and our dielectric material has to be able to withstand the electrical as well as non-electrical stresses together. Even when we are talking about electrical stresses, a material is not going to be subjected all the time only to one kind of stress. You may have a combination of DC and AC stress, DC superimposed on impulse, impulse superimposed on AC. You may have a combination of stresses acting on the material. And therefore, we have to be able to understand how the material or the insulation system will be able to behave under the effect of these composite stresses. Remember, I will discuss this in greater detail later, the behavior of an individual dielectric material does not dictate the behavior of the insulation system as a whole. And since we are really looking at extending the life of equipment, we are looking at long-term degradation processes, which we do not understand as well as we understand short-term processes, short-term failure processes. And because we are looking at more compact insulation design, we are looking at very high field processes. That means there are certain processes which are not of concern at operational voltages, but when you design with very little degree of safety, there might be certain specific processes which take place only under very high fields. And we need to understand those processes, and we don't understand those processes very well. So these are some of the challenges for researchers. But what are we going to learn in this course? What are we going to cover in this course? The first thing is, when you apply an electric field, when you apply voltage across a dielectric, you have an electric field. And this electric field will not necessarily be uniform. So we have to be able to analyze and compute the electric field inside a dielectric material. So I will briefly talk about, in the beginning of this course, I will briefly talk about electric field analysis, and I'm going to limit myself to electrostatic fields because in case of insulation design, that is the primary field that we are interested in. So once we understand what is the electric stress distribution inside an insulating system, we will know how that insulating material is likely to behave. First thing that we have to prevent is the breakdown of the material, not only under normal operating conditions, but also when you have over voltages across the system. So we have to first understand what are the breakdown mechanisms in a dielectric. There are different processes by which solids break down, by which liquids break down, by which gases break down, by which vacuum breaks down. Apart from that, composite materials have other problems which we need to be aware of so that we know how breakdown progresses. Another important thing which I already mentioned is that the aging processes, long-term breakdown processes or long-term deterioration processes inside a dielectric are very important in evaluating and estimating its age or its health, because nowadays we are also interested in condition monitoring, in the sense that we know that materials will fail, we know that electrical insulation will fail, but what we would like to do is we would like to monitor the condition of the insulation such that we have adequate warning before the actual failure happens so that we can take remedial action. So we will need to understand the breakdown mechanisms, and once you understand that these are the fills that you can apply and these are the breakdown mechanisms, how do we prevent that? We prevent that through insulation design. Once you have designed the insulation, how do you know that this design is effective? And the only way to do that is by testing and evaluation. There can be some non-destructive evaluation where you evaluate the properties. We have discussed some of the properties, DC conductivity, loss factor. If you measure these properties, you can get an estimate about the health of the material. But apart from that, you would also have to do some destructive test. And if you are going to do some tests for high voltages, that is, if you want to figure out whether your design apparatus that you have designed is going to be able to withstand high stresses, you need to generate high voltages. So we have to know how to generate high voltages and measure those high voltages so that we know what voltages we have applied, at what voltage has failure occurred, at what voltage has deterioration started. Another very important thing that we have to look at is insulation coordination. Now, when we are talking about power apparatus or power lines, there is a whole topic, a new topic, a complete topic called insulation coordination. Now, if you do not want your system to fail, how do you design the insulation? And there are so many apparatus in your system, and there will be over voltages in your system. So you need a fair idea about the kind of over voltages that you expect at different points of your transmission network, at different apparatus, across the different apparatus that are connected in your network. And you have to design the insulation of all these apparatus in such a way that all these over voltages, different kinds of over voltages at different points can be withstood. And there might be certain equipment which have to withstand higher voltages than the other equipment. But the problem is that can you actually prevent failure? You cannot. There will be outages. So insulation coordination is about trying to design the insulation in such a way that the probability of failure or the risk of failure is reduced. So this is something that we will discuss, how to coordinate the insulation of all the apparatus in our system so that the entire network altogether behaves in a proper manner. So we are going to, in terms of these few things, we will talk about a few new materials. We will talk about a few new diagnostic features that we have, new diagnostic techniques that are available to us and are currently being used or researched for use in the field. And we will talk about how to control fields in non-uniform, when you have very highly non-uniform field distribution inside field apparatus. So these are the things. The syllabus is available to you on the portal, and from the next lecture we will start talking about breakdown mechanisms.